Okay, welcome to this lecture 5 on laws of illumination. In the previous lectures, we had seen the need for illumination, and subsequently we saw how the natural radiation is spread, and based on that we look to have artificial illumination systems as close to the natural illumination as far as possible. And why are we doing all this? We are doing all this because the 80% of our information acquisition is through our eyes, the most important sense, and depends on the illumination levels, and therefore the next two lectures had concentrated on the functioning of the eye. Now, as it goes in any free sphere of science and engineering, it is necessary that we are able to quantify the things which we study, and we also know that the physical processes follow certain observed relationships which we call them as laws, and hence the title of this lecture has been titled as Laws of Illumination. Before we proceed further, we look at the objectives of this lesson. That is to say that at the end of this lesson one should be able to define what is the standard of illumination. As already brought out to you, quantification is a very important thing. It's not enough if I say that I have more light or less light. I should be able to give a value or hang a number to it to say that this is better than that, and that's possible by way of standardization. And the way light is felt on the objects follows certain laws, and that's what we're going to address. The second objective is listed as what is a candela. As we go along, we'll know what is a candela. In fact, incidentally, candela is the standard way of assigning the light output, and as may be understood, it is a variation of the term candle. All of us are familiar with candle. Whenever there is a power cut these days, of course we have emergency lamps, but early days we used to use candles, and that's then there is a term called MSRI, which stands for mean spherical luminous intensity, and one needs to understand that. And as already told, as title, the lecture title, as laws, one of the first laws that is associated with this illumination principles is Fresner's law. So one should be able to state Fresner's law at the end of this lecture. And as has been with many physical phenomena, there is always an inverse square law associated. Recall the mechanics, we have an inverse square law. Recall electrostatics, we have an inverse square law. So it's interesting that most physical phenomena have the inverse square law governing the energy delivery and utilization. So let's look at the laws of illumination, and as I said, before we really go into the laws of illumination, it becomes necessary for us to know how we are going to standardize the light output, and that is to say we are going to hang some numbers to the light. And how do we do that? Because the first source of artificial light has been a candle. The first standard that has been adapted for light output has been a wax candle. However, it is highly unreliable. Recall that in any meteorology or measurement technology, the standard adapted must be stable, must be reproducible from one laboratory to the other laboratory. Hence, it was considered to be very unreliable, which was subsequently replaced by what's known as vaporized pentane lamp. A pentane lamp running on the pentane vapor, that's why it is called vaporized pentane lamp, which emitted light approximately 10 times the original wax candle. This was subsequently taken, which was subsequently in the year 1909 it was replaced by incandescent lamp, and it is compared with a pentane lamp. However, this has not been used much because, as already told, it should be reproducible, which is not easily possible with a incandescent lamp. Hence, there was a move to look for a better standard, and probably in the year 1948 there was a better standard adapted, and as written out here, it was based on the light output from what is called as a radiator. Recall, in an earlier class when we were talking about the physical processes involved in artificial light, we talked about various light output devices like black body, grey body, selective radiator, etc. So, here we have standardized by considering a good radiator radiating light through a small aperture, and the platinum is being maintained at its what do you call solidification temperature, and that has been adapted as the standard. What are the components of this standard? These components of this standard are, as can be seen, number one, a radiator, which is essentially fused thoria, or the words thorium oxide, which is about 45 mm long with an internal diameter of 2.5 mm. So, this aperture is packed with fused thoria at the bottom. This is supported, obviously this is a powder packed, so it has to be put in a container. It was put in a container consisting of a fused thoria crucible, which had a 1.5 mm aperture, and all this had to be kept in a good thermally insulated environment, and this is possible by keeping it in a large refractory container. And the platinum, the pure platinum that is used is melted, and it is to be maintained at what temperature? It is at the freezing or solidification temperature, which is 1773 degree Kelvin. And to do that, the high frequency eddy currents are adapted, and it is observed that this gives rise to approximately 589,000 candles output, light output, spread over a unit surface area, and therefore it was believed, okay, though initially it was of this kind, it was later standardized as the light corresponding to 600,000 units of original thing. Let us have a look at the picture of the standard. As can be seen, this is the primary standard of light. As you can see, there is a opening from where the radiant output is brought out. This has got an opening of about 1.5 mm in diameter, and there is a cubicle which is fused thoria cubicle kept in a highly refractory environment. As we said, it has to be thermally insulated. So, it has got an outer this thing consisting of unfused thoria, in which in this cubicle, as already told, the radiator is a pure platinum which is vertically supported. The crucible had a dimension of approximately 45 mm in length, vertical length, and 2.5 mm diameter, and this platinum is maintained in a molten state, that is at the solidification or freezing temperature of platinum, that is 1773 degree Kelvin. Now, this having been adapted, we said this gives out an output which was close to 589,000 candles per meter squared, which has been made equal to about 600,000 units. So, having said that the primary standard of light is this, in fact today we adapt the light to be this, and any light radiation output we compare has to be with respect to this. Having said this, we redefine our candela, or what we said as the light output due to a original wax candle is the luminous intensity in the perpendicular direction. Obviously, when we talk about the light output, we look at the ability of human eye to perceive the object when light falls on that. So, and this calls for the normal radiant radiation to be considered. Hence, we talk in terms of luminous intensity in the perpendicular direction, which is 1 by 600,000. Recall, we said the primary standard corresponds to about 600,000 units of original candles. Therefore, candela has been defined as 1 over 600,000 of a black body, which is nothing but, here is the platinum, pure platinum, maintained at solidification or freezing temperature of platinum under what conditions? The standard atmospheric pressure. The candela is abbreviated as CD. Okay, that means the candela gives us an idea of luminous intensity or light flux radiating capacity of a source of lamp. That is what it is. Now, we go further, try to express the effect of light flux on the objects. Now, how do we consider an electric system? We have a charge, we talk in terms of the field by talking at any point the effect of this charge on a unit positive charge. In a similar way, one could define the light luminous intensity at any surface. In order to understand this, let us consider a transparent sphere at the center of which we place, which is marked O, place a light source which produces one candela, and consider on this transparent sphere, whose radius is 1 meter, consider a solid angle of 1 steradian. If we consider a solid angle of 1 steradian, it encompasses an area of 1 meter squared on the transparent surface. The normal light output due to this would be standardized as the basic unit of what we call luminous intensity, and is defined, or by definition we call it as 1 lumen. Let us look at it once again. What did we do? We considered a transparent sphere of 1 meter in radius. We took a standard source whose light output is 1 candela, place it at the center of the sphere at O, and then consider the light radiating out of this over a surface area or on the surface subtended by a 1 steradian solid angle. By the definition of solid angle, we know if the radius is 1 meter and the solid angle is 1 steradian, the area encompassed on the surface, which is marked here, would be 1 meter squared. Then the normal light output through this 1 meter squared is termed as 1 lumen, and this is the unit of your luminous intensity. Just as the effect of electric charges is felt in terms of the force exerted by those charges on test charges at any point and the normal direction, similarly the light flux coming out of the source is felt in terms of luminous intensity, and it is standardized, or its unit is by definition the luminous intensity over 1 steradian by a 1 candela source on the surface of a 1 meter sphere is termed as 1 lumen. In that sense, the total flux that's coming out of the source, considering a source placed in all directions about the source, because if you consider all directions, you can think of a spherical surface, and the total solid angle subtended would be 4 pi, and recall we considered a sphere of 1 meter radius. In that case, total area would be 4 pi, and therefore it is said that if we place a 1 candela at the center of a sphere of 1 meter radius, we would get a flux of 4 pi lumens. Okay, that is the thing. So, how do we go about understanding this? We have defined the basic unit of luminous intensity, which is nothing but 1 steradian, the flux coming out of 1 steradian by a 1 candle source is placed at the center of a 1 meter sphere is termed to be 1 lumen, and therefore total flux due to 1 candela placed at the center would be 4 pi lumens. As against this, if I take a source which has I candela, I is normally used to denote certain candle power of a source. This is also called candle power. See, it's very simple, recalling that the first and foremost artificial source has been wax candle. That's how we have got. Let's see how do we go about doing this. Let us consider the solid angle subtended over a certain area is d omega, and then the total luminous intensity is I candela, that is the source candle power is I candela, luminous flux in d omega, if we call it, that is over the solid angle d omega, is termed d phi. Then we have that as I into d omega lumens. Recall 1 candela over 1 steradian produced 1 lumen. If I have high I candela, okay, over a range of d omega solid angle, it will be I d omega lumens, and therefore I say that d phi by d omega would be my I, the candle power. Now, there is another term which we often use with respect to these lamps, because now recall, after we started using electric lamps using thermo effect, thermoluminescence, it's been the incandescent lamps, which are nothing but a filament maintained at a temperature placed at the center of a glass envelope, which means it had the ability of radiating light in all directions. So, in a sense, it could be viewed as a source of light, a point source of light. So, it had the ability of radiating light in all four directions. It means the overall solid angle subtended by the light output is 4 pi, and therefore, the term mean spherical luminous intensity is talked of. Mean spherical luminous intensity, it means luminous intensity when considered in all directions. For a point source, you will find that it is same, equally distributed in all directions. When we go on to the control gear, you can observe, depending on the application, one could orient the amount of light flux radiated in different regions to be varied, and that is where it becomes somewhat important. Now, having said luminous intensity and the luminous flux, now how do we know how much light is really falling on object? And we have to consider the area of the object into consideration, and this is defined by yet another term. In fact, that is what we call as illuminance. See, we have not yet come to laws of illumination. We are in the process of standardizing the light output. We have learned what is a primary standard. Now, we have also learned how luminous flux is defined, and so we say the power, radiating power of a lamp is expressed in terms of the primary standard and is talked in terms of candela, and the amount of light that is coming in a particular zone is talked in terms of the luminous flux, which is lumens, and this luminous flux per unit area is what is termed as illuminance. It is very important because as you go along designing the illumination systems, you will find that we talk in terms of recommended illuminance levels for various applications. That is a very important issue. We talk in terms of lumens per square meter, and this is categorized or standardized as lux. 1 lumen per meter squared is a lux. So, illuminance, if you consider, again observe the diagram shows at the center of a sphere, we are trying to get illuminance at any point on the sphere. So, assumption again here is that the source of light is a point source. Let us say it has the candle power of 1 CD. Then the total flux, considering the radiant in all 4 directions or all directions in the spherically, would be 4 pi. Remember, the area of the sphere is 4 pi r square, and hence the illuminance would be 4 pi by 4 pi r squared or 1 by r squared lux. So, illuminance radially away due to a point source at a distance r can therefore be talked in terms of. So, observe the figure here. We are looking at a particular source deemed to be a point source marked S, placed at a point P, and has a candle power or luminous intensity of I candela, distant from a plane of observation at d units. Then on the illuminance on the surface by definition is I by d squared Lx. Now, in trying to find illuminance, we are looking at the normal light flux incident. It is quite possible that there is every chance of light coming in an oblique direction. So these issues have to be addressed by way of considering how this is governed. But it's time we took at the first of these laws, which we call Fresner's law. This is based on an observation made by Weber in 1830. This is about the way human sense organs respond. Consider a stimulus of intensity I, and let it be having a least perceptible increment that can affect the sense organs as di. The observation made by Weber says that the ratio di to I is a constant. This is under the situation, remember, talking of the way I functions, we said there are certain considerations the way I functions. Fatigue is one important thing. So, this observation says that it holds good under fixed fatigue, attention and expectation. See, there are two things. The eye per se is the physical device through which you allow the light or the information to get into it. But it is the brain that processes and you are able to see. That means there is some amount of expectation. Often it is said you read what you want to read more than what is written, unless it is properly written. Okay. So, what does the Weber's observation say? It says if there is a certain stimulus I and it has a least perceptible increment di that can affect the sense organs, the ratio of di to I is a constant. This is further examined by the Fresner with respect to your illumination, and he has found that there is a logarithmic dependence as far as optic nerves go, and that is expressed as S. Sensation produced by optic nerves has so what do you have? S is equal to C log I by I naught. What is this I naught? I naught is the threshold, that is the minimum luminous intensity that is able to produce any this thing on your eyes. So, there are this aspect has to be kept in mind, that while designing light sources, because any change how it is going to affect our human eyes is dependent on this Fresner's law. The next thing, as I said, the inverse square law, just as in any other physical system, we have this. In fact, is very apparent in even from the very definition of illuminance. We said the illuminance at any point due to a point source turned out to be the ratio of luminous intensity to the square of distance between the point and the thing. So, we find so this is what is expressed in this equation, I am afraid that in this equation 3 it should be Ix is equal to k by dx squared, not k dx squared. To that extent there should be a correction where dx squared is the distance. Now, talking of the illuminance, we considered the light coming in the normal direction from a point source when defining the illuminance or considering the inverse square law in its basic form. But we did mention that it is quite possible that the light from the source may not be radiant on the object, incident on the object in a normal direction. It could be obliquely assigned. How do we go about taking care of illuminance under those conditions? Illuminance is, however, defined in terms of the normal light output, and therefore this is by definition obtained from what we call Lambert's cosine law. So, how many laws we have seen? We have seen there are three basic laws. The first law says that the ratio of luminous intensity to the perceptible change in the luminous intensity is a constant, and this sensation with respect to the human eyes is logarithmic in nature. That is a very important issue. So, you cannot keep on increasing the illuminance, light output luminous flux, and yet expect your eyes to get better and better. So, since it is logarithmic, the marginal increase may be enough. Beyond that, unless you try to have more uniform flux gradient, you cannot get any improvement in the observational characteristics. Second one is actually a direct corollary of the definition of illuminance, which says luminance is inversely proportional to the square of the distance. This becomes more clear. Now, here in this picture, what is it we are trying to see? You observe that there are two planes. One is source plane marked S. It could be an array of lamps which are radiating light in the normal direction, shown by the thick arrows pointing from S towards right. The normal plane with the object plane is inclined at an angle alpha. In fact, we mentioned about Lambert's cosine law. This alpha in the cosine law comes from this angle between the normal plane and the plane of the object. When we write I cos alpha, what is it we are doing? We are essentially taking the total light flux incident on the normal plane. So, that is what it is. You can see that it is at an angle alpha. BB is the axis passing through the object plane on which the light is incident and you are trying to observe. So, it says I itself on that is proportional to I cos alpha. That is obviously you can resolve the light into the normal component and the horizontal components. Now, let us extend this and try to analyze for various situations. In fact, incidentally, this law is also called as a law of emission. Now, this picture out here shows this is a typical scenario. You find a lamp placed or a source placed at point A, and the line BC is essentially a line on the floor, let us say. This can be viewed as a typical room with a light hanging from the ceiling, suspended at a height B from the floor. So, if you go by the definition of illuminance, one could work out illuminance at varying points on the floor and how it varies. Okay. So, this is in fact, apply the definition of illuminance. The definition of illuminance is what? It says, if the candle power of the source is I, then illuminance at the point of interest is I over the distance square. Let us say we look at a point right below the lamp, that is where you have I over B square, which means it has got the maximum normal illuminance. Now, observe, when we move to the point C, the radially outward light rays are inclined to the normal axis, and therefore, normal light flux would no longer be I, but it will be I cos theta. Theta is the angle subtended by the radial output from the source and the normal axis to the point of observation. And what is the distance? Distance is d. So, we find that, recall, this angle can go from theta equal to 0 to 90 at the most. You recall, if the point of observation is B, right below the lamp, what is theta? Theta is 0 in that case, because the radial output light ray and the normal axis are coincident. Theta is 0, whereas when you go along away from the lamp farther and farther, you are going to get theta higher and higher. And we know that when you move from 0 to 90 degrees, cos theta goes from 1 to 0. It reduces from 1 to 0, and that being the case, you have a decrease in your I, normal light flux, as you go away. And illuminance is dependent on the distance between the source and the point of observation. As can be seen very clearly, at the point B, you have the minimum distance, hence, and you have a maximum light flux, normal light flux, which means you have maximum illuminance right below the lamp. Going by this, we can draw the illuminance as a function of your d by, it should have been d by b, it is marked d by n, and it is marked over a distance of what you call from 0 to 3. If you observe carefully, initially for some small distance it is near about the maximum. This can be the curve pertaining to your luminous intensity or illuminance, and as can be seen, it's nearly same as under the lamp, only for a short distance. That is, you can allow or have nearly same amount of illuminance or light flux only over an angle of 60 to 75 degrees from the vertical. That is, this theta which you are observing, beyond that it would give very large depreciation and it would be ineffective. And this aspect has to be borne in mind in trying to have uniform illumination. It is obvious, supposing I am working on a table which is typically 1 meter by half a meter. I would like to have as nearly as possible same illumination level all through, and that is the issue. And if a single lamp may not serve to have completely uniform illumination, and therefore one may have to go in for more than one lamp. We will also see that as against a point source, a line source, recall the fluorescent lamps or tube lights which we use are nothing but line sources of light. And just as we found that light flux is inversely proportional to the square of distance for a point source, we can see a similar deduction that due to a line source would be inversely proportional to the distance as against square here. And if we are able to have a large sheet of light, it would be independent of that distance. So these are some of the things we will revisit as we go along. So now going back to the thing, we take this example, we try to express illuminance along the distance away from the point below the lamp. As can be seen, this is how the illuminance is going to vary. That is very important. We said this shows that in our trying to have the systems, we should keep in mind this angle theta between the radial light ray and the normal to the plane should not be more than 60 degrees to the vertical. Illuminance at B, therefore, is luminous intensity or the candle power or candela in direction AB. Recall the diagram. We had a lamp located at the point A, and right below, we are talking about the point B is right below the lamp, and the height between this point, the height of this source above the floor is B units, and therefore it is luminous intensity direction AB by B squared. Whereas what should be the illuminance at C? It should be luminous intensity in direction AC by AC squared, and which is luminous intensity in direction AB into cos theta by what is AC squared is B squared plus D squared. And you find that the luminous intensity at in terms of your AB one could, so you find this is how it can be expressed, and this is how one has been able to draw this curve with respect to distance. Observe that in this relationship you could bring this B and this is how one does. Remembering cos theta is B by. So what do we get? We get that illuminance at C is nothing but illuminance at B into cos cube theta, or expressed in other words is 1 plus d by b squared cubed. So, this is how, and all this says that illuminance is a maximum right under the lamp and it keeps on decreasing, and the variation is going to be of this nature, and it is best used only when it is kept with the theta within 60 to 75 degrees. Now, having said so much about the way to standardize the light output, we said it is in terms of luminous intensity, which is unit of which is a candela, which is based on the wax candle, later adapted as the platinum or a radiator maintained at melting or freezing point of the platinum in a thoria crucible, okay, which is adapted as a standard, primary standard, which is equal to how much? 600,000 candelas. Light output due to that is 600,000. Now, if that be the luminous intensity, then we define the luminous flux as categorized in terms of lumens, and for a point source we say it emits light in all directions uniformly, and therefore we talk in terms of what we call mean spherical luminous intensity, and total light flux is in all directions, therefore subtends over 4 pi steradians of solid angle, and hence is termed in terms of 4 pi I, where I is the candle power and is termed in terms of lumens. Now, once you have the luminous intensity and luminance, the effect of this on the plane of observation is talked in terms of a illuminance, which is luminous flux per unit area. It is talked in terms of lumens per meter square or lux. Now, all these is governed by set of laws, which we call them laws of illumination. First law is that due to Fresnel, which tells the behavior of eye based on the least perceptible stimulus that affects our sense organs, and which was initially observed by Weber in biological systems, later observed by Fresnel for optical systems. The sensation of the optic nerves is logarithmically dependent. That means increase in light beyond certain level would not really make much of a difference, put in other words. The second law was inverse square law, which is a direct outcome of definition of illuminance, which says it is 1 over x square, where x is the distance, I over x square, that is the thing, and this applied to any arbitrary plane is taken care by Lambert's cosine law of emission. So, having said this, the immediate requirement would be to assess any of the systems that we have, and the measurements or assessment tests methods are in fact called as photometry, and this invariably would have employing a what is called as a photometric bench, on which on one side the standard lamp is placed, IS of eye candela, This could be a incandescent lamp which is compared with the primary standard, which is nothing but a perfect radiator maintained at the temperature of freezing or solidification of platinum, and Ix corresponds to the what you call the test lamp. What we find is a square screen. This is the dark screen placed in the center and which can be made to move, and it is essentially balanced to obtain same level of illumination on either side from this lamp or that lamp normally resident on the screen. From the balance in these distances, one could obtain the value of I. So, this we will look at in detail. That means, what we are trying to do, we move the central screen till such time the illuminance on either side is same. Illuminance, recall, is nothing but luminous intensity by the distance square. So, you have Is by ds square is equal to Ix by dx square. So, this becomes the important, and in fact, more details of these photometric methods would be covered in a subsequent lecture. Coming to the summary of the lecture, we have defined the basic unit of light flux as luminous intensity is a candela, which is the intensity of a surface which is 1 by 600,000th of a black body at the freezing temperature of platinum, which is 1773 degrees centigrade under standard atmospheric pressure. The illuminance intensity over a 1 steradians solid angle by a source of 1 candela has been termed as the unit of flux, which is 1 lumen. Means MSLI is used with all point sources is the average intensity into solid angle, which is the mean spherical luminous intensity in all directions. Luminous flux is luminous intensity into the solid angle. Illuminance is the luminous flux per unit area, and the Freshnel's law gives us the idea of the response of the eyes, which says same percentage change in stimulus from the least amount perceptible gives the same change in sensation. Inverse square law is nothing but the definition of illuminance, which says illumination varies as a square of the distance inversely. Lambert's cosine law of incidence is useful in estimating. Here is the luminous intensity at arbitrary point in arbitrary direction, which is I cos alpha by d. This is cosine law of emission, talks about the candle power. Incidence talks about the luminous intensity, illuminance, that is the lux. Some of the questions that can be addressed from this lecture are: what is the standard unit of luminous intensity? What is MSLI? What is the standard procedure to measure luminosity? Some answers to the previous lecture's questions. Quantity as quality of illumination are important. Why? At present, eye tasks are more and for longer duration, and hence increased illuminance is required. So, illumination also affects psychology, hence quality is also important. What should be the minimum brightness of the surrounding? Brightness of surrounding must be less than that of the object and should not be less than 0.01 foot lamberts. What are the 3 primary colors? As already known, they are red, green and blue. How does aging lead to loss of vision? As can be said, aging leads to decrease in adjustment capability of the focal length of the eye, and higher illumination is required for older people. What is chromatic aberration and why it occurs? It is the reduction in acuity due to combination of different colors. It occurs due to the fact that the eye lens has different refractive power for different wavelengths of light. Thank you.